In the last video, I described for you then that acceleration in projectile motion is only in the y, and that comes from the net forces from gravity, so that acceleration is the acceleration due to gravity. And I emphasized that this always points in the same direction, so that can either be speeding up or it can be slowing down. And the sign only depends on how you've defined what positive is. And I gave you this problem that we're going to start working on, and then I laid out the questions that we want to solve. And here now I'm going to throw in an extra little piece. This is the equations of motion. That's what the EOM stands for. We just get a little lazy in writing that over and over again. This equation here, well, gosh, this is just rate times time equals distance. So this is at a constant velocity times the amount of time I do that velocity is the displacement that I'm going to have. Things that hopefully you've seen in regular day-to-day life before. And then this one here is really restating, oops, I'm sorry, this first part here is restating what this is saying, that the displacement I'm going to cover if I have no acceleration is my rate times my time. If I have acceleration, then I add in that piece. So this 1/2 AT squared gives us displacement, as does rate times time. That gives us the displacement. So whatever my initial velocity is times the time I'm at that initial velocity, well, that's some amount I've got on the graph. So in the graphs that we were doing, it'd be like the straight line where you're just doing a square, the length times the width to get to your displacement. And then we're going to add in however long I'm accelerating, and that gets me to that total displacement. Here is relating velocity in terms of acceleration and displacement. So where these come in handy is the bridge that we use between our x and y components is time. It's going to be the same for both. So if I'm looking at the same snapshot, it's going to be the same amount of time. So if I can find it for one, I can get to the other. And then displacement, kind of depending on what I know or what I need to know, it's going to depend on if I need to use something related to time or something related to displacement. So let's see how this works. I'm going to redraw this picture. There's the ball going like that, and I'm going at 20 meters per second. The ball is going that way, and I know that the height of the table is 1 meter. What I'm going to do for myself, because I know it's going to go this way and it's going to land on the ground, is that I'm going to define down as positive and to the right as positive. It's just my habit. If you want to do it the other way, you can. This is just, I'm saying, I know the direction of the motion is initially to the right for the x, and will be down in the y. And then what I suggest doing is making a list of the parts and pieces that you have. Let's do that in a different color. So in the x, I know that my initial velocity, whoa, you won't be able to see that. My initial velocity is that 20 meters per second. It has no acceleration. If there is no force acting on it, there's nothing that is going to slow it down. So its final velocity is going to be the exact same as the initial velocity. There's that piece. That's why I get marker everywhere. Now, let's see, acceleration, that's the next easy thing to answer for that, is 0. If there's no air resistance, there's nothing slowing it down, there's no acceleration. Our displacement, how far it's going to land from the table, well, that's a question mark. That's something that was asked for. And the amount of time that's going to take, that was also something that was asked for. We don't know yet. But if I come back here, the nice thing about x, when there is no acceleration in that direction, is that the only equation that applies is this one, the rate times time equals distance. Because these two, well, this has to have acceleration. Otherwise, this piece becomes 0, acceleration is 0. Nah, that's not very helpful. I get up here, well, this is a repeat of this, so acceleration is 0. This is just giving me my displacement is my rate times time. And this one too is that it has to have acceleration, because if it doesn't have acceleration, then this piece goes to 0, and my v final minus my v initial is 0, so that's not helpful. So I can straight away write one way that I can, or one thing I can solve for, the only equation I can use to solve for anything is that velocity times time gives me my displacement. Rate times time is distance. Okay. Now for my y, let's see what we have here. For my y, talking about that split second where it's just going to come off the table. I have no velocity in the y because it is on the table. All of the motion is in the x. So my initial velocity in the y is 0. My final velocity in the y, well, that's definitely changing, but I don't know what that is. It's going to be whatever acceleration does to it for the length of time that it's in the air. So I don't know what that is. Do I know my change in height? I do. This is 1 meter. Now, an important note here is that change in height is y final minus y initial. That's how we define this delta thing. So if I have defined down as positive, and in essence what I've done is flipped my axes. So this would be y equals 0, and this would be y equals positive 1. Because I've defined this as essentially my up. I flipped it upside down. So my delta y is a positive value. Just the same as my acceleration going down, I've defined as positive. So that is a positive 9.8 meters per second squared. Now let's take a look at what we can solve for. We have, what did we want? How far from the table did it go? Well, see, that's going to be something related to x. So I definitely need to know time. I don't have that. So look at this. Now this x is interchangeable. Where you see an x, I can also write that as y. This one won't do me any good because this says that the velocity is constant. This one has velocity changing. I know the height. The initial velocity is 0. I know the acceleration, but I don't know the time. So let's see, what can we do with this? Well, gosh, I could solve for time if I wanted. Yeah, heck, that's one of the questions it asks for. So let's go ahead and do that. So let's see, I have my delta y equals v naught t plus 1/2 at squared. Now let's take out the pieces that go to 0. This is 0. So I can go, let's see, 2 times my delta y, and I'm to divide by my acceleration, gives me time squared. So if I take the square root of this, that gives me time. So one of the equations that you see on the internet a lot is that they'll rewrite this as is the square root of 2 times h for the height divided by a. So just be careful here. I've defined these as both being positive quantities. There are times when we're adding and subtracting things that randomly grabbing internet equations can hurt you. Because if later on, if you define that change or that acceleration as being negative, and you leave height as positive, when you add things together, it's going to mess up your answers. So let's see, let's throw these numbers in there then. I get that t is the square root of 2 times my delta y is 1 divided by 9.8 meters per second squared. So if I look at this 1 has a meter in it. I should put the units in there. The meters cancel out. The seconds pops up top. Take the square root of it. That gives me just a second. So that is in terms of seconds. Let's see. Well, I'll just crunch it out. So my t is then 2 divided by 9.8. Take the square root of that. Take the square root of it. There we go. T is 0.4518 seconds. And I'm writing that out. I know that the sig figs I gave you here is just 1 actually for the 20, but it is handy to make sure that you don't introduce errors, to carry through as many values as you can. In fact, that's part of the reason that I wait till the very end to number punch anything, is so I'm not rounding on my intermediate steps. I come here, I have time. I know the initial velocity, so I can actually solve for this. So I know that I was 20 meters per second times the time that it took, this 0.4518. And that will give me, seconds, sorry about that. That will give me, so multiply this by 20, displacement of 9.035. 9.035 meters. So we know this, and we know this, 0.45 seconds. I answered 2 of the 3 questions. The other one is, how fast is it going when it hits? It asks for its final velocity. So I look at this, I'm like, okay, so I know its acceleration, I know its time. So when it asks for its final velocity, I can go here and be like, okay, I can plug in these values. I can plug in the initial value is 0, so its final velocity is just going to be the time times the acceleration. That's rather straightforward. But I need to remember what this v final is that I'm solving for. Let's go ahead and do that over here. That v final, let's say, would equal v initial, which is 0, times or plus acceleration times time, dividing by acceleration. That gives me my time. So that equals, sorry, that's what I get for skipping steps. Let's just write that out, shall we? So v final equals v initial plus acceleration times time. Started solving for the wrong thing. That's not helpful. That piece is 0. So v final is this acceleration of 9.8 times the time of 0.4518. So my final velocity in the y, I'm just going to select, oops, I don't want to subtract that, times 9.8 gives me, v final, there we are, 4.427 meters per second. So what I have now is the velocity in the y when it hits the ground and the velocity in the x when it hits the ground. Neither of these are its magnitude of its final velocity. These are its component pieces. So one way to think about that is if I come over here and here's my ball that hits the ground, so I have this projectile motion coming down. Well, as it comes down, let's see, what do I have? I have some y component of velocity and some x component of velocity. So what I've defined with these 2 values, that I've created a triangle. I have velocity in the x and velocity in the y. So I can come over here. I can go, here is my velocity in the x. That's supposed to be a straight line. Here's my velocity in the y. Well, this value is 20, and this value is this 4.427. What it's asking me for is this velocity, the resultant, the hypotenuse of this 90-degree triangle that I make with my x and y values. So that one then is going to be the magnitude of the velocity is the square root, just using Pythagorean theorem, of 20 meters per second squared plus this 4.427 meters per second squared. Pull all those things together. I'm going to square that one. It should give me 20, almost 20. And then plus 20 squared to the 1/2. And when the ball hits the ground, its total velocity is this 20.48 meters per second, which isn't surprising. This is a larger number. So when I square it, it is going to have more of the character than this one is. So this is only having a small contribution to how fast it's actually going when it hits the ground. This value would be like if you had a radar gun and could put it on the ball as it's in the air. What the radar gun would read is this value. These guys are just component pieces related to the physical motion of projectile motion, which is a vector quantity. And there you have it.